Okay, it's now my pleasure to announce the next speaker is Cosimo Della Santina, who is an associate professor at the TU Delft and also a research scientist at the Dern Aerospace Center. And so he's originally from Italy, had different stations, also at MIT, Technical University of Munich. And in Delft, he leads the Physical Intelligence Lab, and where he's looking into providing motion intelligence to physical systems, which is also what he will be talking about today. And he also received multiple awards in his career, including the Georges Giralt PhD Award and also the IEEE RAS Early Career Award. So I'm very much looking forward to your talk on moving without thinking, embodied intelligence in locomotion.
Thanks, Katja, for the very nice introduction. Thanks all of you for being here. Good morning. I will continue a bit in the direction of the very nice talk of Sarah about talking a bit about embodiments. So if you were here yesterday, a soft robotics keynote, you have already this one spoiled. Otherwise, if you are so lucky to see this for the first time, this is a video that I like very much. What you can see here is a fish swimming against a flow of water. It's doing it very skillfully, managing its own body so that to compensate the effect of the fluid flow. So this is all very nice, and it's something that you will definitely would like to have in your own robot. But then you read the paper and you discover that this is actually a dead fish. And what you observe here is completely the result of an emergent behavior coming from the interplay between the nonlinear dynamics of the fish body and the fluid dynamics of the water. So this is very interesting in itself from a continuum mechanics perspective, but as robotics, it poses us in front of a quite cool challenge, which is if nature can do that, why can't we do the same? Why can't we build kind of zombie robots that can present this kind of motor intelligence without having a brain? So already during my PhD and then later with my group, we spent quite some time thinking about this question. And most of this time we spent looking at it from the perspective of robotic hands. This is not going to be a talk about hands, but at least I want to show one slide because I think it shows reasonably well what I mean with that. This is a robotic hand that we developed with two motors, so 2 degrees of actuations, 19 degrees of freedom. What you see here as no sensors, there is no control loop, and all the behavior that you see there, the 3 behaviors that you see on the right, are the result of the same fit-for reduction generated at the motor level. And this is possible, so this kind of fine movements that you observe at the fingers are the result, once again, of the dynamics of the hands and its interplay with the object itself. So this hand is made of tendons, elastic elements, rigid elements, and quite some theory and data that I'm not going into. But the same building blocks went into developing more recently this robotic foot. What we did here was to try to replicate the windlass mechanism from the natural foot. In the human foot, this is generated by combination of the plantar fascia, the longitudinal arc, so the bones that create the longitudinal arc, and the elastic elements in between. And we used, again, artificial elements like elastic elements, rigid parts and tendons to build something similar. We skip the technical details. But the first thing that you very quickly notice by looking at this completely passive foot is that qualitatively its behavior is already quite similar when you place it on the environment what to a human foot will have. I mean, this is nice, but it's very qualitative. So in order to be a bit more quantitative, we started smashing this foot on the ground, so more or less from this height, and we started comparing the behavior of the ankle of when you use this more complex foot compared to a rigid counterpart. And here you already observe something very interesting, but kind of expected. This is an elastic system, an articulated system. So you have this very nice smoothing out of the interaction forces due to the interaction with an uneven terrain. What I think is much more surprising, at least was for me, is that this doesn't come at the cost of stability. So quite the contrary, the region of support of this foot is quite large, much more large, of a rigid counterpart. And this comes from the fact that, first of all, the foot very nicely adapts to the environment, so conforms to the environment. But secondly, when you move this pendulum, this inverted pendulum, the internal structure compensates, let's say, the forces redistributes, and up to a point in which even the fingers in the tip of the finger start pushing against the ground to counterbalance the forces. So you have some kind of brainless self-balancing behavior that is arising. And this is very consistent across, across grounds, across different initial conditions, etc. So we have a brainless hand, we have a brainless foot, but what about complete brainless bodies? We observed for the fish. Is something that with Josie Hooks we have been working intensively in the last few months. This is a legged system which is made to resemble a quadruped, so a dog more specifically. We take indeed data from dogs, and what we wanted was to generate this kind of very nice running behavior directly from the physics of the system. We built these robots. We have a version with motors, but the video that we're going to see is completely motorless. So this is completely passive. So it's completely a passive locomotion behavior. And what you see there is just the result of the excitation, which is coming from the treadmill. And you can see this is a very nice match with the videos that we started from to extract the data. So these were just a few examples of this space in which you can work with, which you can indeed create, embody some physical intelligence, some motor intelligence into systems that do not have any brain. However, I feel that the real deal, the sweet spot, is when you have such a mechanical intelligence body and you start putting in some computational intelligence. For what concerns locomotion, my group and I have been focusing mostly on two kinds of tasks: steady-state locomotion and explosive jumps. And for what concerns steady-state locomotion, we look at it from the perspective of, again, of nonlinear oscillations, because if you look at someone that's like a dog or a person that runs at a steady state with a steady pace, and you focus on the behavior at the joint level, these kinds of look like low-frequency oscillation. Indeed, what we do is that we start by studying what this system, this multi-body dynamic system can do well by extending nonlinear model analysis. And then once you have characterized the natural oscillation that this system can do, we develop controllers that can excite and sustain this natural oscillation instead of imposing behaviors from outside, prescribed behavior from outside. So I think this is very clearly shown by this video, which is, okay, it's running. Let's see, it's going back. So this is shown by this video. Okay, you are going to see only one of the two. Anyway, this is a segmented leg with springs inside. And what we are doing here, again, is by control, we are exciting this natural oscillation of this leg. You can see on the left a low energy oscillation, on the right a high energy oscillation. These behaviors are remarkably robust to any kind of harassment that you can think of, because, once again, this is just what the robot would like to do. We are just helping it by injecting some energy and stabilizing these oscillations. But this is still quite far from locomotion. It took us a few years to patch together this different oscillation and start observing or creating this very robust, very efficient locomotion and very natural locomotion patterns coming from combining oscillations, and a bit, even few years to get to a complete whole body system that run or prongs thanks to these nonlinear modes, and this is a paper which is in press in these days. So it took quite a few years. So let me skip these. So this was steady-state locomotion. Explosive jumps look like steady-state locomotion, but you have just one go. So you have one shot, and you have, for example, to go as far as possible, or trying to solve some other similar problems. Here, for example, when we look at the problem from the model-based numerical optimization perspective, we do that in the context of templates models. What we do is that we develop template models so reduce order models that contain into them the information of the real elasticity of the system, and then we use numerical optimization to reason on this elasticity to perform optimal jumps, and then we retarget using whole body control. I like very much to do this kind of optimal analysis on systems, on this system here that we have developed, modifying a Go1 robot by adding parallel springs. So basically, in this final system, you are able to quite easily engage and disengage parallel elastic elements. And so you can compare what happens when you have this embodied intelligence given to springs compared to what you don't when you don't. With that, you can generate also all kind of other jumping behavior using similar ideas. And potentially, you can push it even further to even more aggressive jumps, for example, using end-to-end reinforcement learning. You can see some example here of even more aggressive jumps, but the same simultaneously also very precise. And this is a RAM paper which is presented by Vassil at this conference. So to conclude, again, the sweet spot, I believe, is between mechanical intelligence and computational intelligence. And by combining these two kinds of words, we are able, I think we will be able to generate systems that can walk, that can locomote by minimum amount of sensing with simple actuation, but being robust, effective, and efficient. I will take just last few seconds to talk about two directions which my group and I are very excited about in this vein. So one is about considering like these two words together. So right now in my talk, I was presented design the mechanics and then presented design the intelligence. But actually we can do both together, and this what we see here is an example in which co-learn the brain and the structure of the body of this elastic leg to have task optimal systems that locomote, for example. And another thing that we are very excited about is to use more unconventional robots, like continuum software robots, to investigate more unconventional locomotion modalities. So that's all from my side. Thank you very much for your attention.
Okay, yeah, thank you very much. Great talk. Are there questions? Then please step up quickly to the microphone, because we only have 2 minutes, I think. Is there someone coming? Okay.
Really liked your talk, Cosimo. My question was about the soft foot, but I think it relates to a lot of these. A lot of the feet that we see, they have either passive, very, very springy and elastic, rigid carbon fiber blade, or we see something like a series elastic actuator with a controlled, maybe variable impedance or even a fixed impedance. And I'm curious, kind of separate from the impact, how does this affect the amount of like rollover or forward progression, elasticity that as the person is walking with these multiple elastic joints? Yeah.
Okay.
That was a very big question.
That's a very big and very hard question. I mean, the honest answer is that I don't know, but I can speculate. So based on what you see, I mean, I'm talking about a specific foot that I've shown, I've presented. Is the behavior of this windlass mechanism into the natural foot is well studied. And one nice capability that it gives you is that it's very effective in storing the energy.
Okay.
And also, since it stores into this plantar fascia, then you can also use it to do the step. So there is probably something to get there. We didn't get to quantify and test it with this system yet.
Okay. Very interesting.
Thank you. I also have a quick question. In the first part of your talk, when you talked about this, also this foot and also the dog-like robot running, what was it more like an overall bio-inspiration that led you to do that, or did you also use computer models to improve the design, like the methods you showed in the second talk or the second half?
Yeah. So thanks for the question. So what we do in all those works is that we actually collect data from either ourselves or from available data from, in the case of the dog, from the dog running and the others. And then we try to retarget this data, so these behaviors, directly on the mechanics of the system. After some dimensionality reduction and the retarget. So there is some computational aspect in the dimensionality reduction, and then in the retargeting is done using model-based techniques. So using developing models of the systems and then inverting these models to obtain the desired behaviors.
Okay, good. Thank you very much again.